Okay, so at this point we've talked about this idea of random variables. We said that there's two types of random variables. There's discrete random variables and there's continuous random variables. We gave a number of examples of discrete random variables. That is every example that we talked about before, rolling a die, pulling balls out of an urn, the way that we modeled it, looking at the price of a stock. Those were all examples of discrete random variables. And even that formula we gave for calculating the mean is the formula that you would use for a discrete random variable. Now we're getting ready to talk about continuous random variables. And in particular, we're going to talk about one very specific type of continuous random variable, one that occurs very frequently, perhaps most frequently, in terms of the application of statistics, and that's something called the normal random variable, also sometimes referred to as the normal distribution. Now, a lot of what we're going to talk about in the slides coming up kind of riffs off what we talked about when we talked about z-scores, which was part of our descriptive statistics. It came after our discussion of standard deviation. So the first thing I want you to do before moving on with this PowerPoint, what I want you to do is go back to your notes, go back to your test, go back to the problems that were assigned to you in the syllabus. I want you to review that. I want you to perfect that. And then and only then, Grasshopper, will you be ready to move forward with this PowerPoint and start building upon and extending that material.
So, just like before, we observe that every random variable has a probability distribution, a mean, and a standard deviation. Normal random variables, no exception. However, the way that probability distributions are sort of done, the way they're conceptualized, is different for continuous random variables than it is for discrete random variables, right? Unlike what we did in Chapter 4, for a discrete random variable, or at least one that takes a finite number of values, we were able to create a table, weren't we? We were able to sort of make that left-hand column. It said maybe something like x takes the values 1, 2, 3, and 4. Right, and then we put the probability, the likelihood of those values occurring, in a column to the right. Agreed? Well, we can't do that, can we, for continuous random variables? Do we see that? Remember, continuous random variables, they not only take the values sort of 1, 2, 3, and 4, but they take all the values between 1 and 2, all the values between 2 and 3, all the values between 3 and 4, right? Which means that it's impossible to create a table going, right, 1, 2, 3, 4, that lists all the values, right, between 1 and 2, between 2 and 3, between 2 and 3, between 3 and 4. So what do we do instead? What we do instead, right, instead of doing a sort of table, we create basically a graph. This actually goes back to Chapter 2. In fact, if you really want to have a strong understanding of what's happening, if you want to give yourself a heads up for the next two PowerPoints, I would strongly recommend you go to the last two PowerPoints of Chapter 2 and listen to those again. Remember, in Chapter 2 we talked about histograms. And at the very end we talked about how you could take a histogram that has a symmetric bell shape. You could think of it as approximating this thing called a density curve. That is, we ultimately drew this sort of smooth line over the histogram, right? And we used that to calculate probabilities by equating probabilities with area. Right? So it's the same basic idea. Whereas we might use tables or the sort of histogram type approach for probability distributions for discrete random variables, we have to instead draw smooth curves that will sort of determine or represent the probability distribution of a continuous random variable. And in this situation, the probability that a random variable is sort of between two numbers, well, that's going to essentially just going to be the area under the curve that is bounded by these two numbers. It's a very sort of abstract idea, but it will become more apparent and it will become more clear, I promise you, as we work through some examples, which we will do very soon. Now, there are thousands and thousands of density curves, right? There are thousands and thousands of these smooth curves that I could draw, each of them representing thousands and thousands of continuous random variables. However, there's one special density curve, right, of these thousands that we specifically are going to focus on, and that's the density curve that corresponds to a normal random variable, right, or a random variable that's said to follow a normal distribution. Now, just like before, remember, every continuous random variable has associated with it a mean and a standard deviation, just like before. The mean of a continuous random variable is denoted by the Greek symbol mu. In theory, it could take any possible value. The standard deviation of a continuous random variable is denoted by the Greek symbol sigma. In theory, it could take any non-negative value. So at this point, this is really the same as a discrete random variable. All random variables have a mean, denoted by the Greek symbol mu. All random variables have a standard deviation, denoted by the Greek symbol sigma. Now notice I'm not getting into how we calculate these for a continuous random variable. Calculating them is different and requires some mathematical techniques like integration, which you learn in calculus, and is not a prerequisite of this class. So we are not going to have to determine or calculate these are. They'll be given to us in the problems.
Now, with respect to the normal distribution and its density curve, the graph of a normal distribution, it's that familiar, deja vu, symmetric bell-shaped curve, exactly like what we were working with at the end of chapter 3 when we were doing problems with z-scores, and we were looking at things like the weight of a walrus, or maybe the score on some sort of SAT exam, or just some Math 121 exam.
The peak of this bell-shaped curve, the peak is the mean of the random variable. Its fatness or skinniness depends on its standard deviation, sigma. Here is a very crudely drawn, thanks Microsoft Paint, normal distribution, right? It should have a smooth bell shape, but because of my shaky hand it doesn't. But notice how it overall is very tall and thin. Remember, we're equating area with probability. So because of that height, most of the area is sort of packed near the mean, which means that, right, there's a high probability that all the values of this random variable are going to be near the mean. Contrast that with this. This is a normal distribution, still has that should be smooth bell shape, only this is a little bit more squashed down, and because it's been squashed down, that area has been pushed out towards the tails. This is saying, right, that there is a larger probability, there's more area in those tails, so there's a larger probability of observations being farther from the mean. That means more overall spread outedness or dispersion. That means a larger standard deviation. Now, the total area under any density curve, right, mathematically speaking, the total area under any density curve is 1. Right? That's the whole area. Because the normal density curve is symmetric, the area to the left of the mean is the same as the area to the right to the mean, which means that the mean splits the bell curve in half. There's 50% to the left of the mean, 50% to the right of the mean. This is sometimes a useful fact for us to know.
Now, remember what we talked about back when we were finishing up descriptive statistics, when we were talking about z-scores. One of the things that we talked about was this empirical rule. So let's go ahead and review it. The empirical rule was an enumeration of 3 very, very important facts. And what these facts are, what the rule says, is that for a normal distribution, 1, 68% of all data values, 68% of the area, 68% of a population is within one standard deviation of the mean. 95% of all data values are within two standard deviations of the mean, and 99.7%, virtually, but not quite, everything, virtually, but not quite everyone lives within three standard deviations of the mean. That is, it's very, very rare, very remarkable to be more than three standard deviations above the mean, and similarly, three standard deviations below the mean. Now, these numbers are rounded just a little bit. That 68% is not precise, that 95% is not precise, but they're very close, and they're good. They're good working numbers for us to go ahead and work with.
Now, here's a problem. It's just a practice problem. You should have learned how to do this at the end of Chapter 2. This is going back to the walruses that we spent a lot of time talking about. Let's assume, just like before, that we know the weight of walruses follow a normal distribution with a mean of 3,000 pounds and a standard deviation of 250 pounds. Then, right, we can answer questions like this. What percent of walruses weigh between 2,750 pounds and 3,250 pounds? Well, this is the same as asking what's the probability that walruses weigh within one standard deviation of the mean, and the empirical rule tells us that that's 68%. Here's a much nicer picture. It took me a little bit of time, but I figured out how to do this in Microsoft Paint much easier. So there's our bell-shaped curve, right? What this is basically saying is if we took a histogram of a bunch of walruses, if we took a sample of a bunch of walruses, say hundreds of walruses, for every walrus we recorded their weight, and we made a histogram, the histogram would look like this smooth bell shape. It's centered at 3,000. And so if I want the area between 2,750, which is to the left of it, 3,250, which is to the right of it, that area is going to be 68%. That's the same as saying the proportion of percent of walruses that weigh between 2,750 pounds, 3,250 pounds, right? That's going to be 68%. And so this is what we just said. This is essentially asking what percent of walruses weigh within one standard deviation of the mean. Empirical rule says that's 68%. Now, the problem is this. Empirical rule is great, and as we saw at the end of Chapter 2, it could be used in a shrewd way to answer a lot of different questions. However, at the end of the day, it is limited in what it can do. If I were to ask you what percent of walruses weigh between 2,700 and 3,300 pounds, your answer would be like a desperate gulp and a oh dear or an oh my or uh-oh, right? Because we cannot answer this question with the empirical rule. Agreed? This is basically asking what's the probability you're within 1.2 standard deviations, right? If you don't believe me, remember we could use the walrus formula on this, right? By doing 2,700 minus 3,000 divided by 250, we get negative 1.2, right? This is all Chapter 2 review, which is basically saying that 2,700 is 1.2 standard deviations below the mean. So this is asking what's the probability we're within 1.2 standard deviations of the mean. Empirical rule doesn't answer that. It says 68% for one standard deviation. It says 95% for two standard deviations. It does not tell us what the probability is for 1.2 standard deviations, which means that we need a better way of answering these types of questions. We need a better way of finding probabilities for normal random variables. Thankfully, such a way exists, and that's our TI-83 or 84 calculator. We could use our calculators to solve any normal probability problem. This is how we do it. So, very similar start, We hit second. That's the blue button in the upper left. We hit vars. Then we go to normal CDF. Normal CDF. Right? This is actually, I think, on the very top of our list. Now, normal CDF requires 4 numbers or 4 inputs, and they have to be done in a very specific order. It has to be normal CDF, lower, upper, mean, and standard deviation. Normal CDF lums, right? Just like that commercial. You remember it? I'm not sure if they do it anymore, but they did it a long time ago. It would go lums, oh, lums, lums, lums. Exactly. If that doesn't work for you, the mnemonic that I use in my mind is Lahore University of Managerial Sciences, LUMS, in scenic upstate Pakistan. Yeah, Google it if you don't believe me. Read the Google reviews. They are incredible. And you will see that it has a higher Google rating than even the esteemed Westchester University. So, to find normal probabilities, we use normal CDF. We need 4 inputs in this order: lower, upper, mean, standard deviation. Lahore University Managerial Sciences. Now, how are we going to learn, or how do we know for a given problem which numbers to put where in terms of the normal CDF? Well, what I would recommend doing for every problem is essentially drawing a picture. In terms of solving normal probabilities, the best thing that I could say is the time-tested maxim, Appia-buff. A picture is our best friend. Really, it should be Appia-buff. A picture is our best friend forever. And so, if you want to do well in this class, you're going to have to call your used-to-be best friend. You're going to have to, I know it's not easy, but you're going to have to break it off with them, and you're going to have to create a new relationship with a picture, which is what I would encourage you to do. So, if you want to know what percentage of walruses weigh between 2,700 and 3,300, right? Mathematically, symbolically, I would write this like that. The probability x is just the weight of a walrus. The probability that x is between 27 and 3,300. We know this follows a normal distribution. So again, I don't know about you, but the first thing I always do when I'm a little bit lost, when I'm a little bit not sure what to do, I call a friend. And what better friend is there than a picture? And so here's our picture, right? We have that nice normal bell shape. It's centered at 3,000. We want the area between 2,700 and 3,300. Well, we know that we can find normal probabilities with the normal CDF function. So it's normal CDF lower. The lower number is that leftmost bound. When you look at your area and you see where it's bounded, the area is going to be bounded to the left, bounded to the right. The leftmost or lower bound, that's your first number. In this case, it's 2,700. The upper is your rightmost bound of your shaded area. That's 3,300. The mean is the center of your graph, so that's the 3,000, and the standard deviation we were given way back at the beginning of the problem. That's 250. So I put all those numbers in there, separated by commas, and I hit enter.
And so if we put all those numbers into our normal CDF, we should get the following answer. We should get 0.7699, essentially very, very close to 77%. What is this telling us? It's telling us that 77% of the population of walruses, 77% of all walruses, weigh between 2,700 and 3,300 pounds. We could phrase it an alternative way, equivalent, and that is if we were to pluck a walrus at random, again from that population of walruses, that there is essentially a 77% chance that he or she weighs between 2,700 and 3,300 pounds.